In this section, we're going to introduce some symbols and some symbolic logic to go with what we did in the first section, talking about deductive reasoning. So we're going to identify simple statements, express a compound statement in symbolic form, talk about negating a statement, and then talk about conditional statements and necessary and sufficient conditions. So first, let's talk about simple statements. A simple statement is any statement, any sentence that we can make that is either true or false. You can attribute a true or false to that statement. So let's look at an example where we're trying to identify which one of these are simple statements. First statement, this class is Bio 107. Although this is false, this is Math 107. This is a simple statement because I can attribute that false to it. Next one is, does this class cover logic? You cannot attribute the words true or false to that. This is a question. So this is not a simple statement. It is a question. Next one, turning in an assignment 2 days late in this class will drop your total score out of 10 by 1 point. First of all, that is true. But again, you can attribute a true or a false to that statement. It's a little bit longer, but it's still a true statement. It's a simple statement. And then the last one is not a typo. It's this class is. It's not a complete thought. It's not a complete sentence. So therefore, it is not a simple statement. So these first two are simple. The 1 and 3 and 2 and 4 are not simple. Right? This is not a complete thought. So when we're talking about symbology and we're talking about how to represent our logical arguments, we're going to denote simple statements with lowercase letters. And we're going to start with P, Q, and R. We can kind of go on from there in alphabetical order usually. But any lowercase letter will do. So we're going to say a statement P, that might be this class is Bio 107 or something else like that, has a value of either true or false. So now let's talk about compound statements. So just as we can do with sentences in English, we can combine clauses to make a sentence, right, using conjunctions or some other words that we can use to connect ideas. And we do the same thing with logic as well. We have these simple statements. We can turn them into compound statements with connecting words such as and, or, if this, then that, only if, and if and only if. And we're going to look at the and, or, and if then in this video. Another thing that we can do is we can negate a statement, putting a not in the statement, making it the opposite. This is also a compound statement, even though it's a little bit kind of its own special thing because we're not really putting two ideas together, but really just kind of changing one of the ideas. So the negation of a statement is the denial of a statement and has the opposite true false value of the original statement. So if the original statement is true, the negation is false and vice versa. We denote the negation with a little tilde, a little approximate sign. We want to call a similar sign, and we're going to call that the negation. So P and not P, that's what we're going to call this. Not P, the negation of P. All right, so to think about negation can be kind of tricky when we're talking about quantifiers. So quantifiers are all, none, some. These are words that tell us how much we are using of something. Are we using all of it, some of it, or none of it? We have two universal quantifiers, that is all or none. It's either all or nothing kind of thing. or some is a particular quantifier. We talked a little bit about that in the last video. When we are negating a statement with a quantifier, it changes from universal to particular or vice versa. So if we want to make the opposite of all A are B, then if we take not that, that actually becomes, the affirmative becomes a negative. That seems like it kind of makes some sense. Affirmative becomes negative, but the universal becomes particular and vice versa. And it goes the other way around. If we have a universal negative, that becomes a particular affirmative if we take the opposite, if we take the negation of that. And we'll see an example on the next page, which will make more sense. All right, so we have a bunch of statements here, all fairly similar. Find the negation of the following statements. So the first statement is P, the senator is a Democrat. So the negation of that, not P, first of all, is not going to be that the senator is a Republican. That is not the opposite of being a Democrat, right? As there could be other things that a senator could be, a different party. So we really are just going to say the opposite of this is the senator is not a Democrat. That is the opposite of a senator is a Democrat. That's not P. Not Q here. We're going to write it not very good, first of all. We could say that the senator, we're saying the senator is not a Democrat. The opposite of that is the senator is not a Democrat. But that's not very good English. We're going to say instead that the opposite of this is the senator is a Democrat. And that's really the logical idea that if you have not P, that's the same as P. And we'll talk about these kind of things as we go on in the next video. So now we're getting to our universal and particular quantifiers. Statement R says that some senators are Democrats. So we want to find out what is not R. So note that this some senators are, this is our particular affirmative. The opposite of that is going to be our universal negative. So the opposite of some senators are Democrats are going to be that all senators are not Democrats. So doing these negation things can take some getting used to. It's a little bit awkward the first few times you're doing it. But let's look at this statement a different way. To say that some senators are Democrats, we are saying that there is at least one senator that is a Democrat. So the opposite of that is if there's at least one, we're saying the opposite of that is there are no senators that are Democrats. And that's where we kind of get from this like particular some to the universal all. All right, let's try to do this a few more times. Next one we have all are. So we're saying this is our universal affirmative. So the opposite of this is going to be our particular negative. The opposite of all senators are Republicans is going to be that some senators are not Republicans. So again, if you're saying that all senators are Republicans, you're saying that each and every senator is a Republican. The opposite of that is saying that there is just one of those has to be not Republican. The opposite of all senators are Republicans is not all senators are Democrats or all senators are not Republicans. That is not the negation. All right, next one, we have no senator is, that's going to be our universal negative or negation. No senator is a Republican. The opposite of that is going to be, we're going to go from universal to particular. So that's going to be some senators, and we're going to negate the Republican is Republican. So some senators are not Republicans. We go from universal negative to, our first thing is not universal negative, it's universal affirmative. So we go from universal affirmative to particular negative. And lastly, if we have some senators are not Republicans, that is our particular negative. So the opposite of some senators are not Republicans is going to be all senators are Republicans. And I realized I made a mistake on T as well. Let me redo that. This is a negation because of the no. So this is a universal negative. And therefore that we should have that the opposite of no senator is Republican is that some senators are Republicans. This is where it's good to kind of just think about, does it actually make sense? In our minds, because the opposite of not one senator being a Republican should be that there is a senator that is a Republican. All right, so universal changes to particular, vice versa. Affirmative changes in negative, vice versa. All right, let's move on. We can combine two simple statements with a conjunction or a disjunction. We're going to say that and is our conjunction and or is our disjunction. Symbolically, we are going to denote and with this little caret symbol and or with a little V symbol. And they are kind of opposites of each other, and or. So if you want to say P and Q, we're going to do P caret Q, or write that as P and Q. And we're going to show this in the next video, but in order for the statement P and Q to be true, the reason why we use this is because both P and Q have to be true in order for the whole statement to be true. Whereas for P or Q, only one has to be true. And although we're going to talk about this in the next video some more, it's a good time to sort of introduce it as well. And that's the idea of the word or in the English language. So there are actually two versions of the word or in the English language. That is the inclusive or the exclusive or. And note that when we're talking about in math and logic and what we're doing in this course, we will always use the inclusive or. And in some examples, that takes some getting used to because we are very used to dealing with the exclusive or in many examples. So let's see what I mean by this. The inclusive or allows for the possibility that both parts are true. So for example, I could eat a burger or a hot dog. In fact, I could have both a burger or a hot dog. It's not an either or kind of thing. The exclusive or is that either or possibility. I can either start my homework or take a nap. I can't do both at the same time, so I have to choose one or the other. And we talk about either or situations a lot in everyday life and in English language. But we're going to be using or in this inclusive way that you can always have both happen at the same time. So let's look at these in a little more detail. We're going to have two statements here. Statement P Ben is a college graduate, which is true. I'm Ben. Statement Q, Ben is employed, also true. Again, I'm Ben. Find the following statements. We're going to be given the symbolic language, and we're going to translate that into the English sentence. So the first is P and Q. So that is that Ben is a college graduate and Ben is employed. And note that sometimes when you're writing this in an English sentence, you may get rid of that second Ben. Ben is a college grad and is employed. In fact, you might get rid of the is as well. Ben is a college grad and employed. And that's okay. And we have some flexibility in the English language dealing with these logical statements. The next one is P or Q. That is that Ben is a college grad or is employed. And here I dropped the Ben in that second statement, which is fine. And although you may feel differently, I know that my first instinct when I hear a statement like that is I think Ben is a college grad or he's employed is either or. It's one or the other, but not both. But when we're talking about mathematical language and we're using the inclusive or, so this could be both happening at the same time, which in this case is true. All right, next one is not P or Q. And that not only refers to the P, not the whole thing. If it were not P or Q as total, it would be down here with parentheses. And we'll talk about that in a second. So the opposite of Ben is a college grad is Ben is not a college grad. And this is, yeah, and then or we could say that Ben is employed. At this point, I want to talk about this bottom note real quick too, is that the placement of the word not in the English language can be ambiguous. So if I said Ben is not a college graduate and employed, that could mean either that Ben is not a college graduate and Ben is not employed, or it could be Ben is not a college graduate and he is employed. And that's the difference between not P or Q or and Q or not P and Q. I guess I actually did this for the second one. Let's do the last one. We'll talk about that again a little bit more. Here is not P and Q, and it's going to be the exact same statement here. We replace or with and. That's what we're talking about at the bottom. So the ambiguity that we're talking about with the not is not present in mathematics, right? We need parentheses around things if we're talking about both at the same time, if we're negating the entire statement or just that first part. Just know that when we're translating things into English, it gets a little bit tricky because there's so much flexibility in the language and there's some ambiguity built in. All right. Finally, we're going to talk about conditionals. So a conditional is an if-then statement. So let's consider the statement first. If it is raining, then the streets are wet. And there are two statements here that we are connecting together. The first is, it is raining, and the second is, the streets are wet. We could write this symbolically as if P, then Q. And we're going to write that if-then statement as P arrow Q. We're going to say that means P implies Q. If P, then Q. So with all these conditional statements, that's what this is, a conditional statement, there are two different parts to it. First one, the P, that is the antecedent. That's the sufficient condition. That's the thing that comes first. That's going to be the it is raining. The reason it is called a sufficient condition is because of this kind of next sentence here. In order for the streets to be wet, it is sufficient that it is raining. So it is not guaranteed that just because the streets are wet, that it is raining. You know, there's cases where you could have a sprinkler going off or something, and the street is wet because of that. But it is sufficient in the argument to say that if it is raining, that's enough to say that the streets are going to be wet. It's the first thing in our conditional. The second thing is called the consequent or the necessary condition. And what we can kind of say is the sentence that if it is raining, it is necessary that the streets are wet. Right? That initial clause, that if statement, needs that second thing to be true. These words sufficient and necessary are tricky to kind of get your head around a little bit. Just remember that the first part, the if part, is sufficient. The second part, the then part, is the necessary condition. So let's look at some examples here. Translate the following statements into symbolic form. We have three statements here. P is I am healthy. Q is I eat junk food. And R is I exercise regularly. So the first statement is I am healthy if I exercise regularly. So note that this if-then statement is not written necessarily as if-then. If we did, it would be if I exercise regularly, then I am healthy. If I exercise regularly, then I am healthy. So this is going to be if R, then P. And in symbolic form, that is going to be R implies P. If you exercise regularly, that implies that you're going to be healthy. All right, so next thing, if I eat junk food and do not exercise, then I am not healthy. So let's identify the if-then statement here. So if I eat junk food and do not exercise is my entire antecedent. That's the entire first part of our if-then statement. Then I have I am not healthy is the second part. So this is going to be whatever the blank here is implies whatever the I am not healthy. Now let's deal with the not healthy first part. That is the opposite of I am healthy. So that's going to be not P. I am not healthy is a statement, not P. I eat junk food and do not exercise. We are putting together two things with this and symbol. And those two things are going to be I eat junk food, which is Q, and I do not exercise, which is the opposite of I exercise regularly. So, written again, this is going to be Q and not R in parentheses implies not P. Let's do one more. If I do not eat junk food, I am healthy. Note that we don't need the then necessarily in these statements to give this if-then format. It's implied a lot. This is, again, the ambiguity of the English language kind of coming out. So here we have, if I do not eat junk food, then I am healthy. All right, so we have whatever this blank is implies whatever that blank is. So I am healthy, we just P in general. There's nothing different there. And I do not eat junk food is not Q. It's the opposite of I do eat junk food. So this is not Q implies P. So let's look at a few more examples. Translate the following into symbolic form. All mammals are warm-blooded and no snake is warm-blooded. So all mammals are warm-blooded is the if-then statement. If you are a mammal, then you are warm-blooded. And we're going to say mammal could be our P, warm-blooded could be our Q. This is going to be P implies Q. No snake is warm-blooded. You're saying if snake, then not warm-blooded. And actually, you're also saying if warm-blooded, then you're not a snake. Those things are logically equivalent. We'll see that in the next video. So here we'll say snake is going to be R. Warm-blooded, we've already said, is Q. So we could say this is going to be R implies not Q, or Q implies not R. Both of those are correct, and it kind of depends on which way you're looking at it. And last example here, we have two statements. A person obeys the law, P, and Q, a person is arrested. So translate the following into symbolic form. Being arrested is necessary for not obeying the law. So here the necessary condition is being arrested. This is our consequent. This is our second part. This is our then part of our statement. Therefore, the obeying the law is the if part of the statement. So we're saying if a person obeys the law, if P, then Q. And of course, we actually don't want if P. Not obeying the law is our statement. So this should be if not P, then Q. Not P implies Q. For sufficiency, we're saying obeying the law is sufficient. That is the if part. And not being arrested is the then. So we're saying if you obey the law, that's if P, then you're not arrested, that is not Q. P implies not Q. That's similar to what we did in the previous example with the R not Q and Q not R. So necessary means that we're talking about the then part, that's the consequent. Sufficiency is the if part, that's the antecedent. In the next video, we're going to look at some more complex logical statements.